Hello everyone, I'm Tong from CTU in Prague. I'm going to present our oral paper accepted at CVPR 2026 called Global Aware Edge Prioritization for Postgraph Initialization, together with our co-authors Giorgos Tolias, Jiri from CTU in Prague, and Daniel Barath from ETH Zurich. If we want to reconstruct the scene, we could take some photos around the landmark and map them to 3D to localize your camera and figure out their viewpoints, depending on your tasks. So how can we get the output? We can start with classical structure from motion. Given a set of input images, we could build an initial post graph to connect all the images, with the images as the nodes and the relative poses as the edges. Then the post graph is optimized in an incremental way by CallMap or in global manner by GlowMap. We focus on the post graph initialization. To create a post graph, we do correspondence search, in which we do key point detection, feature matching, and running ransack on the image pairs to recover the relative rotations and translations. So where do we run the correspondence search? Do we use all the image pairs? Yes, we can. We could simply use and choose two image pairs, the complete graph. However, it is too costly and it doesn't scale. As a standard practice, we could look for similar image pairs in an embedding space. In the embedding space, we could compute the cosine similarities and take top k images per node. As an example, we have a sparse graph in the end here. It is less costly, but there are two limits. The scores are pairwise, and second, the selection is done in the local neighborhood. So we have a question here. Can we do the score globally instead of doing things in the local neighborhood? Yes, that's what we propose. We formulate the question as a global scoring function, which is a function of the end nodes and their message passed through. So we can get the edge scores at once. In this way, we know globally which pairs should be used first. To ensure the connectivity of all the nodes, we do the selection also in a global way, rather than doing k-nearest neighbors in a local way. We build minimal spanning trees where the algorithm starts from the most promising edges and search a little bit to find a subgraph which connects all the nodes and with the minimal costs. Here we see one example MST. And then we can do the second, we do the third, and the experiments we do up to 5. And then in the end we have, when constructing the minimal spanning trees, we found there are weakly connected nodes. So we propose an updated version of the global edge selection algorithm. Given the first minimal spanning tree, we could clearly see which images are weakly connected. For example, from image 4 to 6, there is a long path with the length of 4 edges, which means the post errors might be accumulated in this way. So before the second round, we increase the direct path, direct edges between those weakly connected nodes and give higher chance for them to be selected. And this is the second minimal spanning tree we get. In this way, we strengthen a bit the weakly connected nodes. So far, we got to know that we prefer global scoring, global selection. How do we get the scores? Given a set of input images, we use frozen DynoV2 plus tuned salad as a visual encoder for node representations. Then the edge features are built by the concatenation of the end nodes. And then we send the edge features and the node features to a graph neural network to aggregate the messages for different nodes, and then we update the nodes and edges in GN. In the end, we run the MRP on top to the global selection. In terms of the training objectives, we do not care about the real numbers of the scores. We focus on the correct rankings of the edges. We obtain the global scores. We run to structure from motion as a supervision, where we count the number of co-visible inliers in 3D, and also ransack inliers. In the inference time, based on the ranked edges, we build multiple minimal spanning trees and then run structure from motion on top. We have learned the method. How does it work in experiments? First of all, we compare the k-nearest neighbor graphs and the minimal spanning tree based graph. Look at the figure. The horizontal axis shows the number of trees used or the number of neighbors. The vertical axis shows the area under the curve scores of the relative poses. At 4K below 2, we could see a huge improvement using the minimal spanning tree based graph than K nearest neighbor. Here we show the aux scores of the reconstructed cameras with the increasing number of minimal spanning trees. We do the experiment both on CallMap and GlowMap. Compared to the state-of-the-art baselines, including Megalog, we improve the accuracy, especially at small case. More interestingly, we applied our method on doppelganger data, where there are duplicates in urban city scenes on the same scenes, which is proposed last year by DG++. We show more registered inlier cameras at the threshold of 5 degrees. We extend the application to WGGT. We aggregate our edge scores to node scores by counting the frequency of the nodes appearing in each node's neighborhood. Given a fixed threshold, we filter out some outlier nodes and run WGGT on the rest. From the table below, we could see it does improve the accuracy by 1 aux score. That's all. Thanks for your attention and look forward to meeting with you at our oral and poster sessions on the last day of CVPR. Thanks.